So today we are going to discuss on the diatomic chain. So previously we have discussed on the monoatomic chain, where we have seen how wave can go in a monoatomic chain, monoatomic crystal. So suppose if we think like we have a material like this, so and we are try to discretizing it into the different portion, then we can consider that it is acting like a monoatomic chain. Like let's say we have a bar where, like maybe you can think that your density of the bar is rho, cross sectional area is A, length of the unit is L, and density is E. Young modulus is E. So we can say that my spring coefficient will be EA divided by L, because if you are thinking that your mass is actually lumped at the midpoint, then the amount of mass is rho into A into L. That's the amount of mass is lumping at that point. And if you think that between these two, what is the stiffness? That stiffness is something like EA by L. So you can think that if we have a continuous bar or rod type thing, and if you want to discretize it, we can think it like there are the masses in the particular distance, and the springs which are attaching to it is like so that in between stiffness is some value. So we can model this thing in the discretized manner as like a monoatomic chain. Now if we think that in this setup, now you think that instead of having all those things same, now like you are having like a bar with the two different material maybe, then how we can able to model it? Now you think how this thing can be thought of. So this mass, so then it is maybe it will be become like this portion maybe, so the black one is rho 1, A1 and L1, and the red one is becoming rho 2, A2, L2, and obviously E2, and this is E1. So what will happen now? How our chain should look like? So wherever you are having that, so we can able to put the black, then black, then black, then black. And what will be the red one? So red one will be red mass, red mass, red mass. So now if you try to calculate the density of the each red mass, that will be rho 2, A2, L2, and density of the black mass is, or sorry, the mass of the black one is like rho 1, A1, L1. That's the mass. And if you think, then in between there will be a stiffness. So that stiffness is basically a combination of both the stiffness. So if I think you are having something like half of, means if you think that portion is something like you are having this, so half of that is your black and half of that is your red. So red will be L2 by 2 and black part will be L1 by 2. So how much will be the stiffness for, so this portion stiffness will become E2, A2, E1, A1, L1 by 2, and the red part stiffness is E2, A2 divided by L2 by 2. Okay, now these two springs are connected. So now how they are connected actually? So if I think that is basically a single spring. Okay, so we can think that if we are expressing this, so it will become like a K effective, and if I think that K effective, so if you see that these two springs are basically in series, so what do you know? 1 by k effective should be equal to 1 by k1 plus 1 by k2. So if I think that this spring is k1 and this spring is k2, so you can write it like this way. So what will be the value? So 1 by k effective will be equal to, if I am just taking that thing in the top, so this will be 1 over u1 into 2 over L1 plus L2 divided by 2 into E2 A2. Okay, so my K effective will be, so you can just calculate it. So you can just calculate that full thing and we can able to place the value of K effective here. So K effective can be calculated like this. Okay, so once we get the K effective, now what can we say? Our new chain, we got the value of K effective, so this is K effective, I can put it, or I can just write it K. Okay, so now if I just redraw that chain, then I will have simple manner, maybe. So like this way. So here we will have M1, 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 M1. This is M2, M2, M2. This is K, 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 K. That way the things is coming. So now if I think that I try to put the nth, so like let's think this is my nth unit cell, so I can draw the unit cell as well here. So if I draw the unit cell, I may choose to draw it like this, which will be repeating like that. So that's my nth unit cell. So that is my nth unit cell. So this will become un, and this is my vn, and this is un minus 1, this is vn minus 1, this is un plus 1, and this is vn plus 1. So what can I write? m1 into un double dot plus k into 2 un minus vn minus 1, that is equal to 0, and m2 vn double dot plus k equal to 2 vn minus un plus 1, that is equal to 0. Okay, so that I am trying to write the equation for this m1 mass and this m2 mass. Okay, any doubt up to that? Okay, so if there is no doubt, then we can think that. So now what we can do, we can implement the Bloch theorem. So how the Bloch theorem will work here? So you can see that this mass and this mass can be correlated, and this mass with this mass can be correlated, because you see we have un plus 1 which is not belonging to the nth unit, and we have vn minus 1 which is not belonging to the nth unit. So what can I write? I can write vn minus 1 equal to vn into e to the power of I mu, and similarly I can write un plus 1 will be equal to un into e to the power of minus I mu. Agreed? So these are the two Bloch theorems, or these are the Bloch theorems used for the two different position of the units. Okay, so now if this is the scenario, then in that case how we can able to rewrite our equation? M1 plus k into minus 1 plus e to the power of I mu into Vn, that should be equal to 0, and this one will become m2 plus 2k Vn minus k into 1 plus ul. Okay, we can write the full thing in that way. Any doubt? Okay, so if we can able to write it in this manner, okay, so we have this one. So now from here, what can I do? We can write the equation of motion in this form, that we can write it in the matrix form. Okay, we can write it in this form. So what happened? This portion, the determinant of this k should be 0, because we can see that these un and vn cannot be 0. So obviously the front part, the determinant should be equal to 0. So if the determinant is becoming 0, what can I write? This into it should be equal to 0. So this is the scenario. So then from here, what can I write? From here we can able to write it that m1 m2 omega to the power 4 minus 2 m1 plus m2 into k into omega square plus 4k square plus, oh sorry, not plus, minus 2 plus e to the power of I mu plus 2 e to the power of minus I mu into k square, that should be equal to 0. So from here we can rewrite it like m1 m2 omega to the power 4 minus m1 m2 k omega square plus 2 into 1 minus cos mu, that should be equal to 0. Cos mu into k square, that should be equal to 0. So from here now we can able to solve for cos mu, because if we take this one then divide by the k square, we can able to solve it for cos mu, or else we can, yeah, so that way we can solve for, so if we know omega, then what happen? We can place the omega. So omega, and these masses all are known to us. K is also known. So once we try to find out for cos mu, we can rewrite that full expression. So this portion, like let's say, so if we try to do it, so 1 minus cos mu k square should be equal to m1 m2 k omega square minus m1 m2 times omega to the power 4. Okay, so this way we can go ahead and we can write out, so what is the cos mu, we can able to find it out. So that can give us the dispersion relation actually. So if we see how the dispersion relation should look like, so if we are plotting it, like if we as we do, like we putting the real of cos mu, real mu and imaginary of mu, so and this is my omega. So you can see that first this thing will go up, so it will reach to the point and then we will have the imaginary value coming like this. So you can see what that once we are plotting the dispersion diagram, so you can find that like first the dispersion diagram goes up in the positive in the real number goes up to pi, and then from pi it once it reach, then the imaginary part is starting. So this portion is like our wave will propagate. So this is propagation, this is attenuation. Again we will see that attenuation will stop, and we will have the again propagation band, propagation, and again it will stop and attenuation will start. Okay, so if you recall, in case of the monoatomic chain, we do not have this in between attenuation portion. This attenuation and this propagation part was missing. So now, so these actually this like two like insertion of the two different material, or you can see that like periodic arrangement of this two material actually allows a attenuation band in between. And if you see why this attenuation band is occurring, this is occurring because of the concept of periodicity. Once actually what happened, once the wavelength of the wave passing through this is getting equal to the periodicity, then this attenuation band is actually coming in place. So that's why actually so that is one of the very interesting point, and this band is known as the Bloch band. So that way you can see, and here you can find that wave will attenuate like this way. So now let's see that if we try to code this full thing and try to see how the things we can able to find out. So we can write a small MATLAB code. So as we have seen the biatomic chain, so now let's see how we can able to code that full thing. So you can see here, like we are writing a MATLAB code for solving the biatomic chain. We have entered here mass 1, mass 2, and we have also given the stiffnesses, and we are giving the omega domain, like from which range to which range we are varying the frequencies, and after that we are solving it here. So here the Z solve and all those comments are used. So you can see now the solution has been completed, and you can see that the positive part is actually showing the real value of the wave number, and the negative part actually showing the imaginary value of the wave number. So this way we can able to get the attenuation band for this. And you can see that top part, so in that real part it is reaching to pi, so it is creating the Bloch band. So and we can see very nicely a semicircular band type here, no peak or anything, because here we are not having any resonance type phenomena. This is like a purely Bloch band. Till today we have found that like first the monoatomic chain, then the biatomic chain. So in the case of the monoatomic, we have seen that, like suppose if we have a rod and we are trying to see that how the wave is propagating through that rod, so we actually show that we are dividing it into the several fragment, and each fragment we are like putting like a spring mass system, and we are modeling it as like equivalent discrete system. So and after that what we do, we say that okay, now we are not having a uniformly means the same system, now rather we are having a periodically repeating system, like these are red, so these are maybe the two different material, change in the cross section, change in the shape, or some of the other things can be possible. So this type of scenario is happening. So in that case what happened, we say that okay, we are having this red, 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 and also our springs coefficient get altered, and so this way we are having a biatomic chain where we are having two different masses lumped, and in that way the springs are also coming. So that is the scenario what we have solved. Now next case is, so these two cases, so we have seen here, once we are looking at the band gap, we see that the solution goes like this and then the band gap started. So once, but here we can see that this thing goes then we are having a Bragg, then again we are having a propagation band, and after that there is a attenuation band. This way the things is happening. Okay, on the so here, suppose if somebody want to use the effect of this band, they can able to make this type of system. They repeat the modulus, they repeat the material or some other things, and they can able to get a chain type thing where the wave propagation can be studied. Now next case is like we can have this thing inside. For example, instead of changing the material one after another, if we can able to make a material where inside we are making a cavity, and there we are putting like a, like let's say you can think of a block type thing where inside we have a cavity, and inside the cavity we are putting a steel ball, and in the cavity we are putting some sort of like a silicon type thing, silicon like very soft some material we are putting, then internally we are having like a steel ball or any metal ball, steel or any metal ball which is really heavy, and this cavity may be made of resin or some other things which are resin or epoxy type resin or something like that. So in that case what happened, we are having a material inside, we are having another very heavy material inside, and they are connected by some soft material. So we can think that way. And now if we are repeating this type of thing one after another like a chain type thing, and we are study the wave propagation, then how we can able to actually model that full scenario. So we can able to think that in the same approach, that our resin like that host one can be modeled like a larger mass, then inner mass is inner, and this silicon type thing which is soft material that can be connected as like a spring. So this type of scenario is going to happen. So these are like a mass m, these are like a small mass maybe mr, these are kr, and these are k. Okay, that way we can able to get that. Now if we think how the equation of motion of that full thing is coming, so in this case, so we are lumping that mass, yeah. So if we think how it is happening, so if I just take like let's say this is my nth cell, so nth cell, so I am just assuming that this one is Vn and the outer mass is Un. So I can write the equation of motion like small mr into Vn double dot plus kr into Vn minus Un, sorry, that is, yeah, Vr into Un, that is equal to 0. Okay, because if we think what is happening here, here it is like this, this is my Un, this is my Vn, and this is my mass mr, and this is the stiffness kr. So that will be only the equation. So how we can able to, so if I just transform it into frequency domain, how can I write? Minus omega square mr into Vn plus kr into Vn minus kr into Un, that is equal to 0. So Vn can be written as kr divided by kr minus omega square mr into Un. So that gives me the basic equation to connect the response of the internal mass with the response of the external mass. We can able to get in this form. Okay, any doubt? If no, then we can go ahead here. So then we got it. Now the next case, so if I just write the equation, other equation, so that will be m into u double dot un double dot plus capital K into 2 un minus un minus 1 minus un plus 1 plus kr into un minus vn, that is equal to 0. That one will come. Makes sense? Because what happening, so maybe I just rewrite it in the next one, so you can think. So this one is moving un minus 1, this one is un, this one is un plus 1, and this is vn, this is mr, kr, k, k, m. So I am writing the equation for this mass. So what should I write? M un double dot plus k into 2 un minus un minus 1 minus un plus 1 plus kr into un minus vn, that is equal to 6. Okay, agreed? So if I write it in the frequency domain, just doing the Laplace transform, I can get this into un plus now recall the equation Vn equal to Kr divided by Kr minus omega square Mr into Un. So what we got? Vn equal to Kr minus Mr omega square into Un. That was the correlation between Un and Vn. Okay. And also, if we think, just recall the Bloch theorem, because they are periodic. So here to here and here to here we can use the Bloch theorem. So un plus 1 should be equal to un e to the power of minus I mu, and un minus 1 should be equal to un e to the power of I mu. So if I substitute that full thing here, what can I get? Plus k into 2 minus kr into So if you see, that full thing is coming in the terms of un. Now there is no vn. So I can again further condense that full thing. That full thing with un, that is equal to 0. So now un cannot be 0. So this term will only become 0. So now if this term is becoming 0, then what we can write? We can write 2k1 minus cos mu should be equal to omega square m minus, or it can be plus kr mr omega square divided by kr into mr omega square, and we can calculate. So from here we can calculate what is the value of mu. So mu in terms of omega we can get. What we were actually basically doing that, so after that we can able to plot. So now once we get that, I will rewrite the expression from the book. So now 2k minus this, so what can we write? We can write 1 minus cos mu should be equal to omega square m by k 2k kr mr omega square divided by kr mr omega square by 2k. Okay, so first, like if I divide it with the kr, I can write what? Minus sign, yeah, okay, perfect. So I just divide with the mr kr, so I can write it omega square, yeah. So first thing, I'm just trying to writing this portion. So here what happening, I'm just writing like mr omega square divided by 2k into 1 minus omega square by omega r square. So what is omega r square here? So omega r square equal to kr divided by mr. So if you can think, I am just taking the kr, or I am dividing the bottom portion with the kr. So the top part kr I am just taking here. So 1 minus mr by kr. So I can write 1 by omega r square. I can get it like this. So this way the things is coming. Okay. So this is done, plus omega square m by 2k we can get. Okay. Now our object, we can think that, now once we write it in this way, we can think that we can express that is like omega by omega r as like eta r, which is basically the frequency ratio, like how much frequency of the resonator, I mean what is the excitation frequency divided by the frequency of the resonator. So that way we can easily able to rewrite the full thing. So omega square m, so here it will come mr divided by kr omega square so we just write. So it was m by k, but I am writing it like m by mr, mr by kr, and kr by kr. So why I do that? Because we can say that this thing is basically my 1 by omega r square, and this is nothing but my stiffness ratio. I can see this is a stiffness ratio, and this is my mass ratio 1 by theta. So what the equation become? Omega square divided by theta into 1 by omega r square into kappa plus 1 by 2, here there is also 2 here, omega square divided by omega r square into kappa divided by 1 minus eta r square. Okay, so what can I get? 1 by 2 kappa divided by eta r square into theta plus kappa so this thing comes. Okay. Perfect, I did correctly. So we can get this expression. So what can I say? Cos mu should be equal to 1 minus kappa eta r square by 2 theta into 1 plus theta by 1 minus eta r square. Got it? So that's become my cos mu. So here, if we think for a particular chain, what are the things we know? If we think carefully, kappa, that is nothing but the ratio between these two springs. Kr divided by K is my kappa. So kappa equal to Kr divided by K. What is theta? Theta is the mass ratio. That is Mr divided by M. Mr divided by M. That is the theta. Okay. So these are becoming your system parameter. So once you have fixed a system, this parameter become constant. So what are the parameters? So what is the parameter on which the mu is depending? That is only the eta r, and that makes sense because eta r is what? Eta r is nothing but omega divided by omega r. Now for a particular system, omega r is constant. So variation of omega can be denoted as the variation of the eta r. So that's why we can rewrite it in this form, and this is a non-dimensional version of writing it. And here we can able to see that once we are plotting this full thing into the eta r axis, this is the real value of mu and this is the imaginary value of mu, we can see that our real part goes up, and once the eta r is equal to 1, once the eta r reaches to 1, then we can see we have a very deep drop, and then it is going up like this, and then we will have like this. So this way the dispersion diagram actually comes into picture. So here that drop at 1 actually shows what? Now whatever the vibration is coming in that frequency, there the internal mass, like what is present here, like if you see that internal mass, or maybe if I just draw it again. So that internal mass is actually in the resonance with the external frequency. So internal mass start resonating, and we all know once like a 2 degree of, so this is nothing but a principally a 2 degree of freedom system. So once a 2 degree of freedom system oscillates in the resonator resonating frequency, then what happens? That vibration of this outer mass will be reduced and vibration of the inner mass will be increased, because here actually the inner mass will oscillate in the out of phase direction. So therefore that actually absorbs the full energy primarily, and outer mass it gets almost, it cannot able to transfer the wave. So that's the prime reason why we can able to see the resonance, and the resonance and means why we can see the attenuation. And if we see the intensity of the attenuation is also very high, so there is a significant level of attenuation is happening. Like let's say for the diatomic case, if some attenuation needs like let's say your 20 units, here maybe the same level of attenuation can be achieved in 3 or 4 units. So in the reality this type of thing can able to save the lot of the space, number of units requirement will be less. So several like the good points are there, but still it is acting on the resonance frequency. So if we want to engineer our band gap, like suppose we want that the starting band gap is some frequency, let's say we somebody told like okay it should start from 100 hertz and it will be completed at 200 hertz, let's say. So then designing, so we can able to design the band gap, that okay where the band gap is going to come. So we can accordingly choose whatever the frequency of the resonator it need to be it is required, and we can place that frequency of the resonator there, and then we can found that okay whatever the wave, maybe it can be acoustic, maybe it can be a mechanical wave, vibrational wave, so those get attenuated in those frequencies. That's a prime important point of the application of this thing. Okay, any doubt? Okay, so if there is no doubt, then we can think further that So in that case, actually several times people are thinking that, okay, is it not just like a putting a tuned mass damper in series? Like you can think that, okay, we are having like capital mass, this is the small mass, this is the resonator, this is the capital mass. So now if we are going like this way, then are we really putting the resonators, means are we not using some sort of TMD, like a placing the tuned mass damper at some locations? Yeah, it is not that wrong to say that, but its effect and why it is called as metamaterial, that point is like much more significant here. Because here what exactly happening, obviously that principle of acting is somewhat very similar, but here some of the other exploration can be thought of. For example, people have tried to find out that, okay, if we try to see what is the effective system for this, means instead of solving that internal resonator there, can we try to just solve a monoatomic chain and try to get the similar type of behavior here? Then what are the changes in the mass or stiffness we have to do? So here the prime point comes, so we can just say it ME and this is KE. So the prime point here is that how we are calculating the ME. So ME calculation will be, so ME is the effective mass. So what do you mean by the effective mass? Effective mass is primarily dependent on the frequency also. So it can change with the frequency. So here, if we try to calculate the effective mass, what we have to do? We have to do the momentum balance. How we can do that? So just forget that K. So if we think that this is the mass and this is the internal unit of MR and this is capital M, this is small kr. We are exciting it with U and we are exciting the internal with V. So what is the equation? Mu means, suppose if I write the equation like a equation of motion for the inner mass, then inner mass will be mr ur double dot plus kr into ur, sorry, that is vr, mr into vr, so kr into vr minus ur, that is equal to 0. So we can write omega square mr plus kr into vr should be equal to kr into ur. That we can able to write. So now what will be vr? Vr will be kr ur divided by kr minus omega square mr. We can say that we get the vr. Now what we are doing? We try to mimic the full thing. So we are having like a m effective by me. So me is also moving in the u velocity. So what we can say? Me u dot should be equal to our momentum of that other thing. So momentum of the other is how? M into u dot plus mr into v dot. Okay, they are not ur actually, sorry, ur point is wrong, sorry, just let me erase that correctly. In the k and m there will be r, but not in the u and v. Okay, so what can we write? So if u equal to u, v equal to u, then what will be v dot? So v dot will be similar manner, same parameter, kr divided by kr minus mr omega square into u dot, same thing will come. So what can we write? me u dot should be equal to m plus mr into kr divided by kr minus mr omega square into u dot. Agreed? What can I do? I can take the m common, so it will become 1 into theta. I'm just dividing by the k, so what will be my m effective? M effective will be m into 1 plus theta divided by 1 minus eta r square. So that's become my effective mass. Now think, if that become my effective mass, then what it tells? So what is theta? Now again, if we think, theta is nothing but mr divided by m. So that is the mass ratio. What is the mass inside divided by how much is the mass in the external unit. That is the mass ratio. And 1 plus eta r square is the frequency. So how we can able to check that whether this makes some sense or not? So if we think that for eta r equal to 0, that means what? And what was eta r? If we recall, omega divided by omega r. So omega r is constant because in a particular system kr by mr is basically omega r square. So kr and mr in a particular system remain constant. So eta r is changing. That means what? What is changing? Eta r equal to omega by omega r. So what is exactly happening? So once we are changing the eta r, that means we are changing the basically omega. And here, if we think that at the frequency equal to 0 or the static point, what is happening? Our omega is tends to 0, or omega is actually equal to 0 in the static. But here we cannot exactly put, so it is 0. So suppose if we put it 0, then eta r will become 0. So this point will become 0. So what will be my equation become? Effective equal to m into 1 plus theta. That means what? M equal to m plus mr, because theta is nothing but mr. So if we see what is the static mass, static mass was m plus mr. Makes sense. So that point is correct. Now what is happening? So if we are putting it in this way, then we can see that my m effective equal to m into 1 plus theta over 1 minus eta r square. So if I try to plot that like me with eta r, so we can start it from 1 plus theta, it will go up, and then what will happen? Then the most interesting thing will happen. Sorry. First thing, it will go up. Once eta r equal to 1, then suppose if we put eta r equal to, let's say put eta r equal to 0.99. So if I put eta r equal to 0.99, then what we can see? This is 1 minus 0.99. That's a very small value. So that small value, theta is dividing by that small value. So that means what happens? This part is actually very high. So that very high value plus 1 is also a very high value, multiplied by m is a high value, very high value. Now what happened? Once we are putting, so that actually tells me that me is very, very high. Now once eta r, if I put 1.01, then what happened? Then you think eta r square is actually very close to 1 but little bit larger side. So this value again is very high, but in the negative, with the negative number, negative sign. So what happened? 1 minus that very high negative number, that is again the negative, very high number. So here we can able to see a sign change, and it will come like this. Now you can see there is a particular point where you are having 1 by theta minus eta r square equal to 0. That means 1 minus eta r square plus theta, that is equal to 0. So this thing happening where? This thing is happening on once eta r equal to root over of 1 plus theta. So once you are putting that eta r equal to 1 plus root over of theta, that point you will see your effective mass of that system will become 0. Make sense? And then you will go there. So now if you think or investigating, then we can see that in this regime our effective mass is actually negative, and that's something really amazing. Here one point we need to be very careful, that negative, once we are saying that the negative mass become negative, we need to always understand here the mass is something like inertia, not the thermodynamic mass of the system become negative. That's not the case. It's the inertia of the system which is becoming negative. Why? Because of the internal resonator, and the internal resonator is in out of phase vibration, and internal resonator is taking the more and more and more like excitation compared to the external one. So therefore, as the resonator is oscillating more in the out of phase direction, the overall momentum change of the system, it seems like negative. It's like we are applying the force in the positive direction, but we can see the change in the momentum in the negative direction, which if we are putting in the Newton's law of motion, we can find that it can only be justified if we are telling that inertia or the mass is becoming negative. So that's why this type of metamaterial is famously known as the negative mass metamaterial. Okay.